so let's have our first example here. So a cylinder contains oxygen at a pressure of 10 atmosphere and a temperature of 300 Kelvin. And the volume of the cylinder is 10 liters. What is now the mass of the oxygen? So first off, let's write down all the givens that we have. So first off, we have the pressure. So the pressure is 10 atmosphere. Okay, and then we have the next one, which is the temperature. Okay, so we have a temperature given 300 Kelvin. So remember that it is already in Kelvin and that is already an absolute temperature. So you don't have to do any conversion with this one. So 300 Kelvin, and Kelvin, the unit of Kelvin is already good. So writing 300 Kelvin, and what is the next one? So we have the volume, of course. So the volume is 10 liters. And for the solution, oh no, the required first, we are required to find what? The mass of the oxygen. So it must be in grams. So remember that we are dealing with oxygen. That is very important. So of course, the formula that we'll be using is the ideal gas law. The general formula is, which is the PV equal to nRT. But remember that N represents the number of moles. So you can replace N here with mass over the molecular weight. Okay, so replacing N by M over MW, which is the molecular weight, and the M is the mass of the oxygen. That is the one that we are looking for. Now, um, substituting the values now. So we have pressure, which is 10 atmosphere, and we have the volume, which is 10 liters, right? And M is the one that we are looking for, so we will leave it unknown. So I'll just write it here, M. And now, what is the molecular weight? Molecular weight of what? Of the oxygen. Okay, so the molecular weight of the oxygen, we already know this one, that is 32 gram per mole. Okay, and of course the R. So what R should we use? Let me just move this a little bit because there's no space left. Okay, so no, not equal. So what is the value for R? So for R, the R that we'll be using is the 0.0821. Now, what is the unit for this one? That is liters atmosphere all over mole Kelvin. Okay, that's the unit for this one, of course. So let me just move this again. And the temperature is already good, so we'll just write it 300 Kelvin. Okay, so just solve this using your calculator. Okay, so just cross multiply this one. Just find the M, but first let's check the units first. So Kelvin has been cancelled and mole is also cancelled. Atmosphere is also cancelled. Liter is also cancelled. So as you can see, we are left with what? Grams only. So the final unit should be in grams. So writing down the final answer, if you use your calcu, all you have to do, I won't be writing the units anymore because we already checked the units and it's already correct. So 10 times 10 times 32 all over the 0.0821 times 300 Kelvin. Okay, so the final answer for this one using your calcu is just 130 grams, approximately 130 grams. So let's move on to the next one. Okay, so let's have the next one, which is an ideal gas is contained in a vessel of unknown volume at a pressure of 1 atmosphere, and the gas is released to expand in the previously evacuated vessel whose volume is zero point 0.5. Once equilibrium has been reached, the temperature remains the same, okay, while the pressure is recorded as 500 millimeters of mercury. So what is the unknown volume of the first vessel? So I already have here two vessels, as you can see, and so what happens here is, let's say that this is our first vessel. Okay, so this is where the gas is originally from. So let's write down the givens that we have. We have the first one, which is the pressure 1. We have P1, which is 1 atmosphere, right? And then before the gas storage is allowed to expand into a previously evacuated vessel whose volume is zero point 0.5 liters. So that zero point 0.5 liters is not your V1 because the one that we are looking for or the required in the problem is V1. So that zero point 0.5 liters is not the um, V1, of course. So that zero point 0.5 liters, that is the original volume of the gas only when it was in the original container or in the first vessel. Okay. And then what happens is you have to transfer it to another vessel to to let the gas expand again. Okay. Then once equilibrium has been reached, so the temperature remains the same. Okay. So um, you have to consider that as a very important. So since we can say that the temperature remains the same, so the temperature is constant. So we can already consider this as Boyle's law, where the temperature is equal to C or constant. Therefore, the temperature remains the same. Okay. So what happens here? Okay. So let's write down the pressure on the second vessel. I think that's already given, right? That is a 500 millimeter mercury. Okay. Okay. So that is the pressure on the second vessel. So what do we do next? So I think we can. Okay, so I think we can write down more given, I think. Okay. So what happens to V1? Okay. So V1 is the one that we're looking for. But how about V2? Of course, the V2, so you already have the gas expanded here, right? And the original volume of the gas is zero point 0.5. And of course, you have to add the volume of the vessel for in the volume of the first vessel, right? So the V2 now will be the original volume of the gas plus the volume of the first vessel. That's why it became V1 plus zero point 0.5. V1 is the volume of the first vessel and zero point 0.5 is the original volume of the gas. I hope this is all clear to you. I hope you understand this. Okay. So that will become our V2. Now, since this is Boyle's law, again, using the PV equal to nRT, the general formula for ideal gas law. Okay, so in this one, all you have to do is just put put all the all the parameters that are constant in one side and all the parameters that are not constant, put it on the other side. Okay, so all you have to do is just separate all the parameters that is not constant and constant. Okay, that's it. Okay, so so this is how you derive the formula for the Boyle's law or any law in that matter, so that you don't have to memorize every formula. So all you have to do is to know which are the constants in every law or whatever is stated in the problem. So in this case, as you can see, T, N, and R are all constants, right? So in this case, they're already separated. Okay, so N, R, T are constant. So here we can write that PV is equal to C, right? Because this is constant, they are all constant. And then all you have to do now is just copy the left side, okay? And just change the subscripts, okay? So you'll have your P1, and then we have V1, all equal to copy, but change the subscript, so P2, V2. And then all you have to do is just substitute now the values that we got. But first of all, as you can see, we have P1 is equal to 1 atmosphere, and then P2 is already, we have 500 millimeter mercury, right? And 1 atmosphere is also equal to 760 millimeter mercury. So you have to change the units now to make it consistent. So it's either make them both atmosphere or make them both millimeter mercury. Whichever you do, you will just get the same answer as long as they have the same unit. Okay, and then let's just substitute all the formulas, all the values. So P1 is 760, V1 is of course V1, and P2 is 500 millimeter mercury, and then we have V2. Okay, so V2, remember, V2 is that is the combination of V1 plus zero point 0.5. Okay, so from this one, all you have to do is just use your calculator, and the final answer that you should be getting is approximately equal to V1 must be equal to 0.9615 liters. Okay, let's move on to the next one. Okay, so let's have the third one. So a child's balloon is filled at 27 degrees and has a radius of 12 centimeter. If the balloon is taken outside on a very hot day, when temperature is 50 degrees Celsius, what is the new radius? Okay, so of course, first off, let's write down all the givens that we have. So we have T1 is equal to 27 Celsius, and we have R1, the radius, which is 12 centimeter. And then if the balloon is taken outside on a very hot day when the temperature is 50 degrees Celsius, so as you can see, there's a rise in temperature which is 50 degrees, became 50 degrees, and we are looking for what? Okay, so we are looking for the new radius. And I think so the safe assumption here is we will consider this as Charles' law, or the pressure is constant. Okay, so because there is no constant involved, no, so P is equal to K, so the pressure is constant. So you can consider this as Charles' law. So writing again the general formula, right? The PV is equal to nRT, right? So PV is equal to nRT. So let's consider again all the separate all the constants and the non-constants, right? So as you can see, N, R are constants, and P. Okay, so I have to put P, N, and R in one side and V and T on the other side. So cross multiplying it, P is equal P all over N R all equal to temperature over volume. So as you can see, P over NR are constants. Those are all constants. Okay. So if these are all constants, so it will become T is equal to V, T all over V equal to C, and then all you have to do is just copy and just change the subscript. So we have T1 all over V1 equal to T2 over V2. Okay, and then, so we already have the temperatures, right? So what about the volume? But as you can see, you have to consider here that this is a balloon. Okay, this is a balloon. Okay. Balloon, of course, we will consider this as a sphere. Now, what is the volume for the sphere? Of course, you already know this one. The volume for the sphere is 4 thirds pi r cube. Okay. Now, substituting this value, so we have now a T1 all over. Of course, substituting V1, that is a 4 thirds pi r1 cube, all equal to T2 all over 4 thirds pi r2 cube. Okay. Now, as you can see, we can cancel out 4 thirds pi because we have 4 thirds pi on both sides. So canceling those out, you'll just left with T1 all over R1 cube equal to T2 all over R2 cube. So now, what are the givens? Okay, so substituting all the givens that we have. So remember for this one that T1 is still in Celsius. So we have to convert this into Kelvin by adding the factor of 273. Right? That's the given is 27. So we have to add here 273 all over R1. Now, what is the given for R1? We have 12 centimeter. Okay, so R1 will become 12 cube, all equal to T2. What is the given for T2? That's 50, right? 50 plus 273 all over is the R2. That is the one that we are looking for. So we will just make it R2. And then you can use your calculus to solve for this one. Okay, so solving for this one, the value for R2, I think I'll just write it here, is equal to approximately equal to 12.3 centimeter. So that is the final answer, and let's move on to the next one.